Hello, this is Dr. David Lubkeman. In this video, I will show you how to model a simple two-bus power system and then, with assistance from ChatGPT, develop a Python-based power flow program. I will be using a series of examples to demonstrate how a chat-based generative AI tool can help you with this type of coding problem. Before we get into the coding, I am going to review the power flow model and the associated equations. We will be looking at a two-bus power system with a generation source, an electric load, and a transmission line that interconnects the load to the source. This circuit would be representative of either a low-voltage distribution feeder or a high-voltage bulk power system. In this presentation, we will be considering a three-phase example where the source is assumed to be ideal with a constant line voltage and frequency. The transmission line represents the electrical distance between the source and load. In this case, we will model the line by a series resistance and inductive reactance. We neglect the line parallel charging capacitance for now. Finally, we have an electric load, which we will model with a constant real and reactive power consumption in watts and vars respectively. This power consumption will be assumed to be constant with respect to changes in load voltage. Once we have the data associated with the generation source, line, and load, then we can perform a power flow calculation. The power flow calculation not only gives us load bus voltage, but line flow values, such as power flow and line losses. This information is used to make sure for a given load that our voltage is in a range needed by the end user and we are not overloading the transmission line. The diagram I showed in the previous slide is referred to as a one-line diagram. A one-line shows the basic connectivity of the power system elements. However, for a power flow analysis, we need an electric circuit model, and for a three-phase system, this would be the circuit model as illustrated here. The three-phase source consists of three individual voltage sources with the same magnitude Vp, but with phase angles that differ from each other by plus and minus 120 degrees. We refer to these as phase voltages, whereas the voltages between two phases of the source are referred to as line voltages. The line voltage magnitude is square root of 3 larger than the phase voltage magnitude. The line model for a three-phase transmission line consists of a series resistance, a series self-inductive reactance XS, and magnetic coupling between phases represented by XM. Note for a transposed line that the mutual couplings are all the same. For a high voltage circuit, the reactance XS is typically much larger than R, but as the voltage drops, the ratio of inductive reactance to resistance drops as well. Finally, for the load model, we have an equal real and reactive power consumption per phase. The single-phase load power consumption is the three-phase power consumption divided by 3. For a balanced three-phase circuit, it is only necessary to model just one phase. The other two phases would have the same voltage and current magnitudes, but with angles shifted by plus or minus 120 degrees. So in our analysis, we will be using the per-phase model as shown here. Note that the per-phase line reactance is the self-impedance minus the mutual impedance. Also, one needs to remember to use a factor of a square root of 3 to relate phase to line voltage values and a factor of 3 to relate single-phase to three-phase powers. To apply the per-phase model, we start by setting variables based on the input data. In this case, we have a complex line impedance, a fixed per-phase source voltage, and a single-phase load consumption. To solve the power flow, we need to solve the three equations shown. The load power and voltage is used to get the load current, which in this simple case also corresponds to the line current. Once we have line current, we can use the source voltage V1 and subtract the voltage drop across the line to get the load voltage V2. This is not a straightforward process, though, since these are nonlinear equations. The load current is inversely proportional to V2, which is one of the variables we're trying to solve for. So how do we proceed? There are many ways to formulate a solution to this set of nonlinear equations. What we will be using is what is sometimes referred to as a Gauss-Seidel technique. In this approach, we make an estimate of the load voltage and use this estimate to obtain the load current. Once we have the current, we can update the load voltage based on a new voltage drop across the line. If the change in load voltage is small and below our error tolerance, then we have an acceptable solution. But if the error is too large, we repeat the process, using the voltage update as our new estimate. After a number of iterations, we eventually converge to a solution. Combining the definition of the input parameters, the iterative voltage solution process, and output result equations shown above, we get this flowchart. Note that it is written in terms of text variables instead of using standard math notation that is used on the previous slide. After the voltage solution has converged, then we output voltage as a line quantity, the three-phase line power loss, and the real and reactive power delivered by the generator. We will test our program code using the two-bus case shown here. Note bus type SW denotes a swing bus, which is an ideal voltage source. PQ denotes a load bus. This test case shows a bit more data than we need right now, but we will use these data fields in future presentations as we make this case more complex. The solution for this two-bus power system is shown. These results were obtained using a pre-existing power flow program. For a source voltage set to 230 kV, we get a line voltage magnitude at the load of 211.68 kV with a phase shift of minus 4.68 degrees. So now that we know how to analyze a basic two-bus power system, let's shift our focus on how we might apply AI. Generative artificial intelligence chatbots based on large language models such as ChatGPT provide the user with a natural language interface for generating text, code, images, etc. using generative models in response to prompts. Many of the well-known AI engines are already trained on datasets that include power engineering technical material in both text and video format and code examples found in open source repositories. The AI engines are also trained on Python programming and the available Python libraries. This makes using a generative AI chatbot like ChatGPT a good starting point for developing power system application code for either coursework or work-related applications. We are going to look at 3 examples in this presentation. The first example involves requesting a power flow program based on a quick request with minimal input. It may turn out we get a useful response without much upfront work. The second example utilizes a more detailed request with input in terms of code requirements. If necessary, we can add new requirements as needed. Finally, the third example uses the power flow flowchart developed earlier in this presentation, where we explicitly tell the AI what algorithm to write code for. As we work through the examples, we will review the pros and cons of each approach. In this first example, we will ask the AI chatbot to create a Python power flow for a two-bus power system. Most of this request is focused on describing the system topology and data parameters for the voltage source, transmission line, and load. The only program requirement we give is on the accuracy of the bus voltage. The program output in terms of load voltage, line loss, and power flow is provided in a separate section. In these examples, we will be using ChatGPT as a generative AI model. This screen shows the entry of the request into the chat box. The response provided by ChatGPT starts out with some explanatory text on the coding steps. The program code is in a separate screen, which can then be copied and pasted into a Python environment. The chat output in this case also includes additional comments on the code itself. When we examine the code, at first glance, it looks as if we might have a working power flow. The program properly defines the circuit parameters as included in the chat input. However, when we look at the code algorithm, we see that the voltage is not iteratively updated as discussed earlier. The program simply computes a voltage based on a first iteration. Let's see what happens when we copy this Python code into a Jupyter Lab cell and execute it. You can use any Python integrated development environment to test this code, but I'm using Jupyter Lab in this presentation since it provides me with the means for capturing and documenting our coding examples. The video description includes a link for you to download either this code in the Jupyter Notebook format or as a commented Python code. When we hit Shift-Enter to execute this code, we see that it runs with no errors. Unfortunately, we get the wrong results. Besides the voltage being off, there are significant differences in the losses and power flow. So there are other issues with the code besides a lack of an iterative approach. Rather than trying to modify this code, let's repeat our ChatGPT request using the same query. When we look at the code from the second request, we get something different. The generative AI model is not deterministic in the sense that a given input request will generate the same results. So if we do not get an acceptable code response from the initial query, it sometimes helps to rerun it several times to get a better starting point for debugging purposes. The code for try number 2 looks similar, but now there is a tolerance factor and iteration limit defined. We also see a logic loop set up to iteratively update voltage until the voltage converges to within the tolerance factor. Finally, this program code outputs our requested results as defined in the ChatGPT input query. Now let's see what happens when we paste this code into a Jupyter Lab cell. The program executes and does give us results. Unfortunately, it is still not working properly since these results do not match our benchmark. We could make a third attempt at a ChatGPT query, but let's take a closer look at this code in more detail to see if we can debug it instead. Taking a closer look at our try2 program code, we see that it uses the NumPy library. In this case, a NumPy function is used to get the square root of 3 since the square root function is not built into Python. The system parameter definitions appear to be complete and accurate, however. If we move down to the program code further, we see that voltage is set as a line voltage, but our calculation model requires a phase voltage. So the first change we need to make, change 1, is dividing the source line voltage by square root of 3. Next we see we have a comment about calculating a load impedance which is not used. So change 2 is to flag this comment. In the next line that defines load power as S load, note that our model requires this quantity to be in terms of single phase watts and bars. But in the input parameters, this was defined in terms of 3-phase megawatts and megabars. So change 3 is to divide this load power by 3 and then multiply by 10 to the 6th. Moving further down in the code to the initialization of load voltage, the variable name denotes a per unit value. However, we are working in terms of volts, not per unit quantities. So change 4 is to modify the name of this initial voltage estimate to be V2 old. We will use subscript old to denote an estimate and new to denote an update. Moving to the iterative loop, change 5 is to rename V2 per unit to V2 old. In our convergence check, let's also make change 6, which is to normalize by V2 new. Once the per phase voltage has been calculated, we will output the load line voltage in kV. So change 7 is to make sure we are using V2 old and multiply our result by square root of 3. Scrolling down further, in our current calculation, we make change 8, which is renaming V2 per unit to V2 old. Then finally make change 9, which gets us to line losses in terms of megawatts by dividing watts by 10 to the 6th. Now, when we rerun the debug code, we get the correct values that match our benchmark. Now let's work through a second example where we provide more information to ChatGPT. In this example 2 request, you could see that I am providing much more detail on how the power flow is to work. I specified that I want a Gauss-Seidel algorithm and also make it clear whether the input voltage and powers are line or 3-phase quantities respectively. I also required that I want to use a per-phase model and work in terms of phase voltage and single-phase power, specifically in terms of volts, watts, and vars. I also limit my solution to not include unnecessary approaches, such as using per unit and making use of matrix techniques. Note that providing this level of detail requires more experience in formulating the power flow code. It is also not necessary to have all these requirements worked up in advance. One could start with example 1 and add these requirements one by one until converging to an acceptable code output. So just as we did before for example 1, I entered this example 2 request into ChatGPT. We will use a new chat session in this case. And for the response, we can see that ChatGPT provides us with Python code just as before. We also receive additional explanation about how the code works. Looking at this code, we see it uses a C math library instead of NumPy to give us a square root function. We also have source voltage defined as per phase in volts and load as single phase in watts and vars. So we don't get the data conversion errors that we saw in example 1. Within the iterative loop, V2 new is used to represent the update, while V2 is the estimate. A for loop iterates over a maximum iteration count and jumps out of the loop when error tolerance is reached. We also see that voltage is converted to a line value in kV and powers are converted to megawatts and megavars before being printed. Finally, the code prints out the required results. Let's now test this code by pasting it into a Jupyter Lab cell. We see that the code executes without error. However, we see a small discrepancy in the expected results. When we take a closer look at the code, we see that when updating the current, there is an error. Current should be equal to S conjugate divided by V2 conjugate. So let's go ahead and fix this and rerun the program. Now we get the correct results. Our second approach resulted in much less debugging. So by putting more effort into program requirements, we can generally save time in the debugging process. In the third and final example, let's explicitly tell ChatGPT how we want the algorithm to work. We will input the program flowchart discussed at the beginning of this video. So all ChatGPT needs to do is map the numbered flowchart steps into the Python programming language. So as before, we enter the request into ChatGPT using a new session and get the code in the same format as before. In this code, we use the Python CMath library for the square root function. What is convenient about providing the flowchart is that the variable names now all correspond to what we defined beforehand. This makes it easier to check our code. The iterative voltage calculation is implemented with a while loop, which exits when the error tolerance drops below our criteria. Note to avoid infinite loops, we could have added a maximum iteration check, such as the one used in example 2. After the voltage is obtained, we compute the voltage, line loss, and power flow in the correct units and then print. To test the code, we paste it into a JupyterLab code cell. After executing, we see we get a code error. It turns out there is no conjugate function in the CMath library. If we want ChatGPT to correct the code, we can simply cut and paste this error text back into the query window. ChatGPT will assume that the error be addressed in a code update. Now we get an updated code that utilizes the built-in conjugate method that can be applied to complex numbers in Python. We then paste the second try code back into a JupyterLab cell and execute. Now we get the correct answer for the PowerFlow results. Another useful function of a generative AI model is that it can also be used to refactor code. Refactoring involves reworking the code to make it easier to read and adding more detailed comments. To refactor our PowerFlow code, simply ask ChatGPT to refactor the code as shown here. We now get an updated version of the code, which will be our final version. Looking at this code, we do see more extensive commenting. Finally, we execute the refactored code in JupyterLab and make sure that it still works. In this presentation, I have shown how we could use a generative AI tool such as ChatGPT to write power systems analysis code. In the first example, we did not put much effort into the query, but then had to put much more work into the debugging. In the second example, I showed that if we put more effort into writing program requirements, that we get better results with fewer errors to debug. However, this requires experience in properly formulating requirements. This is also often an iterative process where you give it your best initial effort, but keep adding requirements until you get a code result that you think you can quickly debug. Finally, in the third example, I set up a flowchart with the variable names. For this approach, you need to have the skill set to write this type of detailed flowchart. This presentation just scratches the surface of how you can use generative AI to write power systems analysis programs. Hopefully, it's provided you with ideas for how to use tools such as ChatGPT for your programming projects.